Good morning, everyone, and a warm welcome to this BCB webinar introducing CSUM, the carbon accounting tool being developed by IBioIC and partners. My name is Kim Cameron. I'm one of the business engagement managers at IBioIC. Before we begin, just run through a few quick housekeeping points. This webinar is being recorded, and we'll share the recording on the Bioeconomy Cluster Builder website shortly after it runs. If you can post any questions that you have throughout the webinar in the Q&A box, we'll come to those. We've got a dedicated Q&A session after the main speakers. And if you could remain muted unless participating in that Q&A session. So we'll run through the agenda. We'll be together for around an hour and a half this morning. We'll begin shortly with an introduction to CSUM from Ian Archer, the Technical Director at IBioIC. This will be followed by a look at Catalyst Carbon Accounting and Data Challenges from Elliot Johnson-Murphy of the University of Strathclyde and CTO of Catanetech. And then Rudy Primrose, Director at Firefinch Software, will look at the software development process for the CSUM tool. And as I mentioned, then we'll have some Q&A and then we'll close around about 11:30. So for those of you not familiar with the Bioeconomy Cluster Builder, it's a collaboration between Innovate UK, KTN and IBioIC. And it has two main goals, the first of which is to raise awareness of the applications of biotechnology and highlight its capacity to improve environmental performance and resource efficiency. And secondly, to support the development of new value chains using biotechnology by connecting people and resources. And so a key part of communicating the environmental benefits of switching to biomanufacturing is understanding the carbon savings that these processes offer. And recognising this, my colleague Ian Archer and others have been developing a bespoke carbon accounting tool, which we're going to look at today. So with that, I'm not going to pretend to be able to tell you any more about the tool. I'll leave that to the experts and I'll hand over to Ian.
Thank you, Kim. Right, I'll try. So are we sharing that okay, Kim? Can you just confirm that looks all right?
Yeah.
Excellent. Good. Thank you. Right. Okay. Good morning, folks. So yeah, this morning I'm going to be talking to you about this the new tool which is in development at IBioIC. I think I would be stretching things to say that we have that you're going to leave here with all of your carbon accounting problems solved. But we are using this as an opportunity to talk to you about where we are with the process and also to look for help and partners in developing this a bit further. And I'll come on to that a little bit later on. So we started this process. Actually, I shall start by saying something about IBioIC and in particular our skills program at IBioIC. We run a core professional development program for our PhD students and our master students and others actually in the program, which involves a lot of techno-economic training, I should say. And the way that one of the courses, as an example, one of those courses that we run for the students is in process costings. It was something that the membership of IBioIC had requested. The industrial partners were saying they would like to see students coming out of their training programs with their masters or PhDs or even HND students with some understanding of how to put together a cost for a particular opportunity and how that might work, to give them that kind of commercial basis and actually help them to compare different options from a cost perspective. So we developed a course for the master students initially, actually based around something that looks a bit like this chemical scheme you can see in front of you right now. Actually, it turned out not to be a very good course in the first instance. It didn't get very good feedback from the students. They were thoroughly confused and didn't really get what was going on. So we thought a bit more about how we could operate it, and we decided what we'd actually teach them to do was cost cupcakes, because everyone loves cupcakes. Everyone gets what cupcakes are about, and so actually the course now is focused on teaching the students on how to model costs within a cupcake manufacturing business, and then obviously alluding to the fact that actually many of the or all of the principles associated with how much a cupcake costs can then be applied to other processes. So you start with a recipe with lots of raw materials. You've got various inputs of energy and capital expenditure and other resources, including people that go into the model, and eventually you can work out how much it costs to make however many cupcakes you think your business can churn out in a year. And actually that's turned out to be a really successful course, and one that we've really enjoyed teaching, and we are very happy to offer that course to anybody who is interested. And we usually try and reserve places when we're teaching the students to people from industry as well coming in, because they always add a really interesting perspective to the cohort that we're teaching when we run that. So feel free to get in touch, contact details at the end if that's something that might be of interest. But coming back to the story here, what it occurred to me while we were teaching this, and also in talking to many of the IBioIC members, that actually there was something in here around carbon accounting as well, in that much of the data and information you need to pull together a cost model is actually the same information you should probably need to try and work out a carbon model for your process. So I started my career as a process chemist. I worked in Grangemouth for Zeneca, and the scheme in front of you right now is actually the one of the last projects I worked on in Grangemouth. And what we would do when we were looking at processes like this was, we would always have multiple options for for which route we would take for the various bits of chemistry. I'm focusing in particular, and I'm looking here at the stuff at the top at the moment, this blue piece here, which was the piece that I worked on. I'll come on to the color scheme in a couple of minutes and tell you a bit more about that. But what we would do often to begin with were paper exercises effectively of multiple different routes and try and work out which ones look like the cheapest before you'd even got anywhere near the lab. And that gave you a huge amount of information before you even started spending vast resources on lab work. We do paper exercises to work out which routes look more promising and then maybe focus on one or two of them. And so, for example, in particular, I could take this stage here, this second stage here, this what we call stereoselective reduction. Apologies for the chemistry on this slide for those non-chemists in the audience, but this is nothing compared to what you're going to see from Elliot in a few minutes' time. So brace yourselves for that one. But this is a relatively straightforward looking piece of chemistry. We were just reducing a ketone to an alcohol. And actually what we did was use the biocatalyst for doing this. But we did have different options. We could have used some in-house technology for doing that reduction using a metal catalyst. And the paper exercises showed that actually the biocatalytic reduction, if you get it to work, should work much better. And Bob Holt's team down in Billingham, at what was then Avisia, did a cracking job on developing this process. And we used to put around about it was about a ton of this material going into a huge bioreactor in a yeast fermentation to do this chemical reduction, about £1 million worth of substrate going in. But the original work on this was done as a paper exercise cost model to try and work out which option was more appropriate. And it occurred to me, I don't know of anybody that is actually trying to do this from a carbon perspective. We think about optimizing in terms of cost, but we don't really think about optimizing chemical processes or any processes, bioprocesses, in terms of their carbon emissions. And I felt that the industry was in need of that kind of approach for various reasons. And the most important of them is that the chemical industry is the largest user of fossil-based materials, fossil oil, gas, and coal, actually. I read yesterday in a report that it's associated with, the chemical industry is associated with 8% of global carbon emissions. And in fact, it's the third largest emitter of CO2 after cement and steel of industrial outputs. And the reason why there's that discrepancy between the largest user and the third largest emitter is because about half of the carbon input ends up in the products, but the rest of that carbon is emitted as CO2 from the energy used to convert one chemical into another. And I'm going to try and explain that in a kind of schematic way in a minute. But the other side to this, and what we see from our industrial members at IBioIC, two of which are named on here, GSK and Unilever in particular, they are desperately committed, or they're desperately trying to reduce their emissions of the products they make, and are committed to net zero by fairly early, fairly near future, actually in 2030, given how long some of these supply chains are to set up. That's not very long at all. So the likes of GSK, AstraZeneca, Unilever, L'Oreal, other companies like Croda within the supply chains are committed to net zero by 2030. But the challenge here is that when you start to look at the emissions associated with this, so AstraZeneca have estimated that 97% of their emissions are actually scope 3. And what that means is those emissions are in their supply chain. So scope 1 and scope 2 emissions, I hope most people probably understand this, but I will reiterate it just in case people aren't quite sure what the scope 1, 2, and 3 differences are. But scope 1 are your direct emissions. So these are the emissions you get when you heat your house at home with gas, or you put petrol in your car and drive down the road. It's literally the CO2 that comes out of the exhaust of your car or of the flue of your boiler. Scope 2 are the next ones where somebody else has done that to generate electricity. So that's your power companies generating electricity, but they've emitted CO2 in order to do that. And then scope 3 is everything else. It's everything that's in your supply chains. And so it's actually relatively straightforward to calculate your scope 1 and scope 2 because they're effectively your energy bill, really, if you understand what your energy mix is. But the supply chain, those scope 3 emissions are incredibly difficult to handle. And if we come back to that same scheme, and the main reason for showing you all this detailed chemistry, it's quite clear when you look at this screen and you understand how this supply chain works, why AstraZeneca's emissions are mostly scope 3 rather than scope 1 and 2. And actually, within this particular supply chain, this is about 20 years old, this chemistry now. It's for AstraZeneca's rosuvastatin drug, and it was the process that was operated by various companies. Essentially, AstraZeneca just did that last step. They brought in this final step of chemistry, this in red here. That was what was done on the AstraZeneca manufacturing site. Everything else in this chemical scheme was outsourced to the fine chemical industry, effectively. So these bits in blue at the top here, we operated in Grangemouth and as I mentioned earlier, at Billingham for the stage 2 at Avicii, and we did this piece at the bottom in Grangemouth as well for this part of the molecule. And then we would pass on those molecules to other companies who did the rest of the chemistry, who eventually got to this molecule, which was what was brought on site at AstraZeneca down in Avalon, and this final step of chemistry was to take it to the final drug molecule and do the formulation. There were I think there were at least 3 companies operating different versions of this process at the top. Each had their own proprietary way of making the molecule, and I think there were 2 making this one, and there were several companies in this supply chain. So this incredibly complicated supply chain is very typical of the chemical industry, particularly the pharmaceutical industry, and you could write an equivalent map, I think, for many products of the sort that Unilever would make, where they're bringing in chemicals from different places, not manufactured by Unilever, but then formulating into the products we understand as Unilever's products. And Neil Parry from Unilever has said in a recent BB meeting that that Unilever are concerned, or they're concerned, that the supply chains are not ready yet to catch up with. They're not running at the pace that's needed for Unilever to meet that 2030 target. And I guess I'm delighted to see these big companies at the top of the food chains pushing these targets and making these targets for themselves. But a different way of viewing what that really means is it's an instruction to this type of supply chain, and it says to this supply chain, if you want to sell to us in 2030, you're going to need to be net zero, because our whole supply chain has to be net zero. You're at least going to have to be able to tell us what the carbon footprint of your products are. And as we understand from talking to all of our industry members, nobody's really in a very good position for measuring that kind of carbon footprint. And that's where we came in to think, well, actually, if we take in some of the thinking we've got, and I mentioned earlier on around the kind of process costing teaching, and then think about that in terms of carbon, maybe we can bring something there. And we've had a lot of encouragement and support from members in IBioIC, from the very biggest companies, the likes of GSK and Diageo and Croda, right down to the very smallest startups. And you're going to hear a little bit from Elliot as kind of effectively as somebody who's on that path as well at the other end of that journey. So as I said, we view the basic principle around CSUM is that this is a cost model. It's just in a different currency. Another way to think about it, as you're going to see, is it's really just a chemical engineering mass and energy balance. I don't think it's that much more complicated than this, but as you're going to hear from me, and you'll also hear from Elliot, the numbers, it's difficult to find the data and the numbers and how to use that data properly to pull together a sensible carbon footprint. But the principle behind our tool is that fundamentally, the carbon footprint of a product or a stage would be, or a stage of processing, is the embedded carbon footprint of all the raw materials going in, scope 3, plus the carbon emitted from the energy used to convert the raw materials to products, scope 1 and 2. So that's kind of where that's really the fundamental kind of guiding principle behind this. And our tool aims to allow you to do this calculation and creates a carbon footprint for a product, or potentially just for a stage of a product. So I've got a couple of wee sketches that I hope kind of illustrate what I mean when I say that. So apologies for the kind of crudeness of this sketch, but I didn't really want to, I wanted to kind of make it easy for people to follow because it's in terms of the basic principles. So, we have companies in the IBioIC network who are interested in making products from seaweed, products like alginate, for example, or other high value compounds from seaweed. So you could imagine, if we think as a theoretical process here, the stages we need to go through from taking taking seaweed from the sea and eventually getting to a product. To begin with, the seaweed here actually has a negative carbon footprint. It's absorbed carbon from the atmosphere in order to form this biomass. We can harvest that seaweed, and that takes some energy. We need some fuel to do that in the boats or however we're going to harvest it. Bring that onto land, and we've got a big pile of wet seaweed, and then we've got different processes we have to operate. We've probably got to dry it. We have to shred it into the right pieces. We then and that takes some energy in terms of heat, maybe some mechanical energy in terms of shredding and milling. And then we maybe have to do a solvent extraction, for example, to bring the product out. And then there's some embedded energy associated with the manufacture of that solvent. And then finally, we may be filtering off the product or however it might work, or maybe evaporating some solvent. So there's other energy associated with mechanical energy, pumping or moving materials, and then maybe heating again to that final product. And so essentially, we've got this balance of negative carbon at this end and then adding in extra carbon as we go through this process. And ultimately, that should allow us, if we can work out the carbon footprints of all of these stages, all this energy, plus the carbon footprint associated with any raw materials coming in, like the solvent, then we should be able to work out a carbon footprint of the product. And that's basically the principle behind where we came from with this as a tool. If we take a chemical industry example, again, this is a very crude picture, but this is one where we may be making ethylene oxide from ethylene that's come from, say, shale gas or natural gas. So initially, we start, the oil and the gas is there underground. It doesn't have a carbon footprint. It doesn't have a negative or positive carbon footprint at that point. It's there, but it takes some energy to get it out of the ground. We have to separate out the gas, maybe separate out different gases to get to ethane. That ethane would be cracked into a mixture of ethylene and hydrogen. Obviously, you can use some of that hydrogen to bring back energy, but there's a huge amount of heat goes into these processes. The ethylene itself can be oxidized. That's going to need some other reagents coming in. So there's some embedded carbon in this to get to your ethylene oxide. So the same principles apply whether we're talking about bioprocesses or whether we're talking about chemical processes. It's energy, it's the carbon associated or the emissions associated with the feedstocks, and then the emissions associated with the energy you need to convert those feedstocks into those final products. Now, as I said, I started my career as a process chemist, so I understand the kind of inputs that these companies, or the kind of data that some of these companies might have. So we're trying to build an app that actually fits with data and existing knowledge and working practices that exist within the industry. And I think there are at least, at the extreme ends of how I want users to use this tool are, if you have an existing process where you have a plant and you have some information, real data from the from an existing plant, I think we can probably carbon footprint those processes based on raw material inputs and on real energy uses that we really understand. And there's going to be all sorts of information from things like, we can get raw material inputs from things like the bill of materials or the process instruction sheets. We should understand a lot about energy usages from things like the engineering line diagrams, and obviously we can account for some waste. And ideally, what we're going to end up with here in that type of situation is identifying exactly where within a process the carbon emissions are highest. So even though we won't necessarily get the most precise number at this point, we should at least be able to identify which stages are the most carbon inefficient, I guess, and what is it about that stage that creates such a big problem. So Elliot is going to talk to you in a bit about some catalysis, and some of the numbers there are quite staggering, where you look at where the real significant impacts are, and it makes it much clearer where you can actually focus your development. The other place I would like to see this used, which is a slightly different situation, is where I described before, where you're at a much earlier stage of development. You may not even have gone into the lab yet, but you're looking to compare options, or compare route options, or compare different options for processes, and then try and footprint what the differences might be between different options from a carbon perspective as well as from a cost perspective. So it's everything. I think I think you can continue to use the tool to try and keep optimizing as you go through the development process, from your initial paper exercises and spreadsheeting right through to actual manufacturing. And I think we always get asked, and I would be happy actually if someone can tell me that someone's already doing this, because it will save us a lot of hassle, and we can just move forward and start doing this in reality. In practice, though, I still haven't found any tools that can do what we're trying to do. So there are tools available for life cycle analysis and modeling, and the most obvious being things like SimmerPro and OpenLCA. And these are great tools, and they rely on background data sets like EchoInvent. In practice, though, they're only used by LCA professionals, and they're not really used by development scientists or engineers. And so they tend to be used much later in the process. They tend to be used as a kind of as an academic study of an existing process or an existing opportunity, or to model something that's already in manufacturing, and it might give you a feel for where some of those emissions are in existing manufacturing, but not at the level of detail that we're talking about here. And neither can really take process data and then create a carbon footprint from it. They don't really work like that. They work back into existing databases like EchoInvent, which is the background data set that both of those tools tend to use. And as you'll see from Elliot's talk, and maybe in a bit of a wrap up at the end, we've got significant concerns about how EchoInvent gets used, in particular the way that data is averaged in EchoInvent. And after Elliot spoke, and I think it'll probably be clearer why we think this is such a big problem. And I think in practice, actually using average data is very inappropriate for this type of analysis, because I think you lose so much of the granularity. And Elliot's got some really nice examples for that when he talks in a minute. And there are also huge gaps in EchoInvent. EchoInvent is actually terrible for chemicals. So it gets updated once a year, and it is the database that most people seem to use, most industry use. So some of the big companies we've spoken to say, yeah, that is the data set they tend to work with. Has huge gaps, and as an example of just how small the data set is in terms of chemicals, its last annual update added just 38 chemicals. So when you think about the vast amount of chemical information is actually out there in the literature, or then it becomes really challenging to find that information, which actually gives a problem. It complicates the use of a tool like ours, because it means you do have to keep going back through your supply chain to understand what's going. But we will use EchoInvent as some of the base data, because some of that data is useful. But as we say, we'll come up with we'll talk about some of the problems associated with that, maybe in Elliot's talk, and then a bit later as well. So I'm my slide is not working. Well, it's not last slide. Here we go. So I think what we want to do ultimately, we want a tool that kind of takes, as I said before, it's going to look a little bit like this, where we start with, for example, something like an engineering line diagram of a plant. This is actually a plant that's a citric acid manufacturing facility, line diagram here. So we would click on an individual vessel, and then from that vessel, we would start looking at the inputs to that vessel. So raw materials going in, and I'm doing a bit of a mismatch of processes here, because this is another process I'm going to talk about in a minute, which is actually the very, very first process I ever worked on in industry, in a minute. So we look at the raw materials going in, and we look at all the energy inputs. And from there, we go look up data in EchoInvent, and where we can then pull that together to understand what the carbon footprint would look like. And there is a big irony in here that we're using the EchoInvent database as our backstop, because it's actually the gaps in the EchoInvent database that mean, and the kind of the issues around averaging in the EchoInvent database, which means that this tool is necessary. So if I just give you a quick example, there are 5 chemicals that go into this process. We have malic acid, methanol, sulfuric acid, sodium carbonate, and a solvent called MIBK. And of those 5, only 2 are in EchoInvent. Only methanol and sulfuric acid are in EchoInvent, and there tend to be average data across continents for methanol or for sulfuric acid. So they don't really take into account the differences between different manufacturing options and different efficiencies, and even energy uses between different countries and the energy mix. Sodium carbonate's not even in EchoInvent. Sodium bicarbonate is, so maybe you could make an estimate based on that if you wanted to, but malic acid and the solvent MIBK aren't in there. So actually, that means we have to go back one step in terms of our processing and make some estimates of what the carbon footprints of those might be. And we can do that, and we can use our tool for doing that as well. And I'll talk a little bit about that, how that's going to work in a minute. So We've got a prototype tool, and Rory is going to tell you in a little bit about how that tool came about. We're very grateful to Firefinch for all their support and how they helped us with this. And as you can see, it doesn't quite look the way I want it to look right now. It's not going to look at its final version, but this is kind of where we think it's going to be. So you start with a blank page and you draw a process flow diagram of what your process is going to look like. And in this particular example, this process flow diagram is actually different vessels. So this is an example of Cellucomp's process, actually. So this is Cellucomp's process for converting sugar beet pulp, so animal feed, into very high value nanocrystalline cellulose. And so the various steps around the process are in here about how that works. And that's really what the tool looks like. And so we've got different vessels in here, but you could have this set up almost like you could have a temporal separation. So you might have different operations in the same vessel, and you've got various inputs of materials going in, and then you click on the vessels and you can put in information about the energy mix on there as well. So that's something we're working with Firefinch at the moment to improve how we input the energy mix data in there to make it much easier for people. But it does give a feel for how this is going to look. And we've done this. So we have at least got a couple of examples now of where we tried to use the tool in anger. It's good. I'd say it's clunky. I don't think it's fair to call it what Rory would say is a minimal viable product yet in the software jargon. I think what we have is a prototype. I think we're probably a month or two away from having something which is a minimal viable product we'll work with, and much longer term in the future. We'll talk a bit about how we might use this much longer term in the future. This is going to be a piece of software that can be rolled out. In the meantime, it's going to need a lot of hand holding from the developers and from us, I think, to use. And that's where we're coming from as a request now. So actually, funnily enough, where we're talking about bioprocesses, I think they're easier to model than some of the chemical processes. And so where we have what I'm looking for here is actually people to get in touch where they think they might have a use for this tool. But remember, and I'm managing expectations here, it's a tool in development. It will give you some information and it will give you a good idea of carbon footprints, but it's still quite clunky as it stands at the moment. It's not a polished, finished tool just yet. But if you have bioprocesses that you're interested in particular, where you've got ideally real data from a real plant that you're working in, so actual manufacturing data, that's great. You may only have data from lab work, that's fine too. It may be that things are just you have information we can estimate or reported from literature, and we can try and put some numbers together to help understand carbon footprint in your process. But actually remember that actually you would also be helping us to develop the tool for future users in doing that. So we're very happy to try and collaborate with people if you have that information. I think for bioprocesses is a little bit easier than it would be for some of the chemical processes, and for mainly because these tend to be slightly more kind of black box processes where we're adding some energy to some biomass, so a kind of biorefining operation like I described a minute ago with the Cellucomp process. For chemical processes, it's slightly different, I think. But we can probably, because there's such poor data in the literature, I think we're going to develop a tool where actually we can start thinking a bit more generically about how processes operate. We can take a stage here. So if I look at a piece of chemistry like this was the very first process I worked in industry, we can think about, well, what's the fundamental thermodynamics of one of these transformations, for example? So if I take that step in the middle, we're doing a reduction of the two ester groups at the end to two alcohol groups. Actually, when we talked, when we did this, because we were looking to take this out into the plant, we had real data from laboratory-based calorimetry that tells us how much energy is released in this process from those calorimetry experiments. And that's done for safety purposes on scale up to make sure you don't blow yourself up when you mix these chemicals together. And I'd start to understand how to operate processes. And so that data, it does exist behind closed doors for much of the chemical industry. Unfortunately, I think most of that data has now been lost in various moves between as ICI became Zeneca and Zeneca became any number of different companies in between. A lot of this information does exist in industry behind closed doors, but isn't available. So if you have information on where you would like to do this and you have some calorimetry data already, I think we can do some carbon footprinting for you. Ideally, that's the ideal situation. If we don't have it, we can start looking at reported data on some of these energy associated with this chemistry from literature, and that will allow us to make really good estimates of the carbon footprint for particular stages. When we look at other parts of the process, like the evaporation stages and heating or whatever, we can add in ideas or add in calculations on the footprint associated with all of the operations with a particular process. And I can even get, if we've got the data, we can calculate it from some fundamental thermodynamics, even down to kind of bond energy levels if we don't have any data at all. So there are different ways we can mix and match the energy associated with a process, and then estimate its carbon footprint. So that's where we're going now. And again, if you have information or you look to try and model something like that, please get in touch, because I think that's where we want to go, and that's where we're taking this next. So some contact details here if you want to get in touch with me. I'll leave that on the screen just for a second. That's my there's my business card there, which gets my LinkedIn account as well, through that QR code. But please get in touch either through me, through info@ibioic.com, or Kim Cameron at ibioic.com if you think there is something where you think you might benefit from helping us to develop this tool. We'd really appreciate any and support, in particular if we're able to share some data, or if we're able to use your real data, will make a big difference to the overall tool development. Obviously, well, that's going to be done in strictest confidence and not to be shared. So I'm going to finish now just with some acknowledgements. And number one, I need to acknowledge Megan Lewis, who is a PhD student at the University of Warwick. She's part of the BBSRC's Midland Integrated Biosciences Training Partnership. She's a plant immunologist as her PhD. But this is a really big shout out to the BBSRC's PIP program, the Professional Internship Placement. So Megan worked with me for 3 months back in 2021 and did the fundamental coding associated with this tool. So we'd started out with some spreadsheeting, and Elliot's going to kind of give you a bit of a background on what those spreadsheets start to look like in a minute. But Megan basically converted those. She taught herself to code in the first week of her PIP, and then finished by the end of it with a really nice piece of software that had something like 8,000 lines of code, and came to us as a non-coder and went back to her group as the expert coder. And Megan really deserves a huge amount of credit for delivering that, and I'm really appreciative of that PIP placement. It gave her a chance to spend 3 months focusing on developing a really interesting new skill for herself, and she's still involved in development of the tool. You're going to hear a minute from Rory at Firefinch, who have done the work here, and I must thank Rich Addison for his input into his work to convert Megan's basic code into something which is now actually usable and much more kind of with a much nicer user interface. And then Jamie Cleaver has been brilliant at helping us with a lot of the chemical engineering calculations, and Jamie's still involved. And finally, Strathclyde for helping with some funding on this and ongoing support in terms of how we're thinking about bringing this to market, however market might be, whether that's a service that's operated by IBioIC or whether it's actually something which becomes a more commercial operation. So Kim, I'll stop there because I'm sure I'm over time, and let you pass on to the next to Elliot, I think is next, isn't it?
That's great. Thanks, Ian. Thanks for this. A good bit of background to the tool, and also a bit of a call to action there, how you can help support the development of CSUM. So that's great. I'll hand over now to Elliot Johnson-Humphrey, Research Associate at the University of Strathclyde and Chief Technical Officer of Cata Nitec, who's going to look at the Catalyst carbon accounting. Okay, I'll hand over to you, Alex.
Hello, can you hear me?
Yep, all good.
You can see my screen, I hope. Can you see the screen?
Yep, yeah, it's all good.
Wonderful.
All good, Elliot.
Yeah, so I'm here today to talk a little bit about Catalyst carbon accounting. So sort of where are we and what have we still to do? We talk a lot about in-process chemistry, sort of the inputs and the outputs, but I'm going to try and sort of highlight the catalyst component of this. How much does this really contribute to the overall emissions, at least, of the process? So I will likely know no one really bar Ian and some of the panel members I know earlier today. So I'm going to do a brief introduction of myself. So I, like many people, when they sort of discovered chemistry and became interested in it, I became interested at the point of sort of clandestine chemistry, which was sort of non-legal synthesis of various sort of compounds, because it was very broad out of the box thinking, which I really liked, and sort of tickled that part of my brain. And then as I did my sort of degree, I developed a keen interest in both inorganic and organic chemistry. And in my final year, I was lucky enough to do my master's project with Manfred Brockman at the University of East Anglia, which, for anyone not particularly familiar with the universities within England, that's in Norwich, so Norfolk way. Lots of sugar beet, lots of pigs, and lots of pubs. Highest pub per capita in the UK, I think, still currently. Basically, I developed a keen interest in the applications of organometallic chemicals, so specifically within technology and as well as catalysis. So the materials I made in my master's project were photoluminescent, so they could be used in OLEDs and LECs, which are like emitting electrochemical cells, so things for screens and other weird and wonderful things. And little did I know back then that I was actually one of the bad guys, because I was using palladium to catalyze some of the reactions to make the ligands for the components of the sort of gold materials I was making. I then later started my REA PhD with Dr. David Nelson at the University of Strathclyde, which was investigating structure and activity relationships in nickel. So that's kind of understanding when you stick things to nickel, how does it affect sort of nickel's properties, and what does that then induce in reactions or other areas of chemistry. Essentially, one of the key things that I noticed almost immediately within the first sort of 6 months of my PhD was if a reaction failed, it didn't break the bank, as I'd come from working with gold, which was famously fairly expensive, and it's the thing that we used sort of before most forms of money was trade. It was non-perishable. Was when I sort of killed a reaction that had nickel in it, all it really meant was that for anyone familiar with Sisyphus, it just meant that the boulder rolled back down the hill and I had to push it back up the hill again. It wasn't really that much of a problem. In the later half of my PhD, I invented a novel, sort of safe, scalable way to produce a very large number and still growing number of active nickel catalysts, which are particularly useful to a large number of reactions, both industrially and small scale ones. I'm currently a research associate, as you may have heard earlier. I have been finishing up my PhD for quite a while. Anyone that has done a PhD recently knows that you'll be writing up for quite a long time, COVID among other things. And I'm proposed to be the CTO of Cap on the spin out, which should hopefully be within the next year or so. So where am I currently? So when I first started doing the commercialization stuff, the best sort of USP of our materials, as I saw it from somewhat a layman's perspective in terms of the business stuff, was that the nickel materials were more cost effective than the current platinum group metals that were being used. However, customer discussions that were had across 3 or 4 different sectors really sort of stressed the importance of sustainability over cost, because if it is significantly better for the planet and less emitting, cost is really not a problem to them as long as it does what they need it to do. So what do I need to do in order to gather the information needed? And then, like, where do I go for it? What can I do? Can we even find this information? What should be done about it? So again, brief introduction about catalysis. Just, I don't know everyone's background, so just I'm up to speed, if you will. Catalysts are essentially tools that conduct chemical reactions, and they improve the process efficiency. So this can usually take place by reducing their input requirements. So this can be anything from reagents, space, materials, energy, or the time of the actual process. Over 80% of manufactured products use catalysis in at least one of their steps, so they are hugely important. They themselves are typically made from refined or precious materials. So think about metals, organic molecules, enzymes, all of these sorts of things we use to make things. And generally speaking, increased access to more differing catalysts make processes more accessible, as long as it's not more iterations of exactly the same thing. Yeah. And then I'll bring the scope in a bit more. So we'll move towards more sort of my end, where I'm familiar with things. So this is metal catalyst summary. So this is essentially, there are 2 sort of camps, if you will. One of them is heterogeneous, which are out of phase. So these are usually solids and they operate on liquids or gases. And then homogeneous, which is more the stuff I'm familiar with and worked with, which acts within phase, where we essentially stick something to a metal which allows it to act within solvent. Both of these have been predominantly sort of dominated by platinum group metals, and I hear you all asking, what is a platinum group metal? So are these 6 metals highlighted in red bottom, so ruthenium, rhodium, palladium, osmium, iridium, and platinum, and they are all some of the rarest materials in the world. And earth abundant, or first row transition metal chemistry, which is one of my particular favorite interests, has been more of a use, was like case by case rather than generic, because it was usually cost motivated, where you could afford to use cheaper materials because the materials you were making didn't have a higher margin, something similar. However, within recent years, the demand for these actually more sustainable and also cheaper materials is growing. And I'm also probably going to talk your ear off about nickel if you give me the opportunity to, because it's one of my personal favourites. So why am I here today talking to you about this? Essentially, Emma, so someone I work with, sort of connected myself and Ian, who you've already heard from, along with David, so my sort of line manager and previous PhD supervisor. And we sort of sat down one afternoon and decided to comb through some literature and try and pick something that was relatable and addressed both all of our collective needs. So we wanted to investigate a palladium process, and we sort of came across this, I'm going to say simple two-step procedure that we were interested in. It's the synthesis of an API, so an active pharmaceutical ingredient. The QR code should work. I stuck that up there because it saves people sort of having to frantically type in the DOI. So feel free to move that to afterwards. But it's for this specific OPRD paper, which is very good, as they have lots of different process scales, which is important. So we initially started with the first step. And as I sort of alluded to, nothing is ever simple. So when we first looked at this, we recognized that the inputs and your outputs are not really the thing of interest here, because these will change every time you swap a process. And the sort of tools for the process are really the thing that we're actually sort of more interested in here. So we tried to quantify the catalyst against sort of solvent activating agents and other materials present. The sort of dichotomy or the issue we run into here is that the tiny amount of palladium that we're using, so less than about 1% relative to a lot of the other material, is responsible for the very high level of productivity we see here, but it's also responsible for the vast majority of the CO2 impact, so less than 1% of it. It's responsible for 86% of the emissions of those three different materials. And I should say at scale, the isopropanol that's used, so the IPROH, for those that aren't familiar, they use 270 litres of that. So you could have 6 times as much solvent in there to bridge the gap between the 1 kilogram of palladium catalyst that we're using, which is phenomenal, if you ask me. And this really addresses something that I'm sort of personally, I'm interested in, because I like it when small actions can actually have quite a substantial impact. So swapping this catalyst seems like to have a very large impact at scale. So where did we start? I'll quickly talk through this and then let the video run through fairly quickly. Ian and I had both sort of gone through, so eSpaceNet, for those that aren't familiar, is a very good portal for accessing patent data, and we'd found a patent for the synthesis of triphenylphosphine, because as Ian has alluded to, it wasn't within EcoInvent, so we had to do a first principles point of view. So we had to take chemicals from within EcoInvent and try and build a system. So I'm going to let the video play through now. But we have our procedure, we built our plant on the right, and the sort of diagram on the right is a specially designed reactor which essentially chops up the sodium. We went through all of the multiple different steps to get out our figure, and then the next step was working out a synthesis of palladium, which I'll show you in the next slide. And this is the EcoInvent data that we plugged from the database as well that we were using. And from this, we were able to essentially show you what I'm about to show you, which was that the huge amount of emissions associated with that catalyst are almost all the first step. So it's the extraction process and then the refinement of this metal that is responsible for such a large amount of material. And again, because I'm going to talk to you about nickel, I've snuck nickel in comparison's sake. In the process, we have palladium, which will be ppm level or slightly higher than that. This will then get refined through a diagram, which I'll show you later, which is a bit of a hellscape. We then have to turn this into a salt that's usable. We then use a very large amount of ligand and excess. We reduce it using a very high nitrogen containing material known as hydrazine, which is very emitting to produce, which essentially just rips off chlorides, produces nitrogen, a bunch of other stuff, and we produce this material. And it's worth highlighting here that the 9% or so palladium present in that product, because of all the other stuff that is currently stuck to it, is responsible for as much as 95% of the emissions. And that again comes down to the fact that nickel produces 8 kilograms per kilogram of CO2 when it's extracted and refined, hydrazine 13.6, and triphenylphosphine, as we calculate, is about 8 to 8.5 kilograms per kilogram. And then when we look at palladium, it's 21.5 tons per kilogram of metal. which is phenomenal. It's a very, very large difference for that. And it's because it doesn't really exist anywhere in large quantities. And where it does, you still have to do a lot of work to actually get it out. So one of the problems I came across within EchoInvent, and I think Ian and I, when we were working on this, felt like we were going a little bit crazy, because we started seeing patterns emerging when we were comparing data against one another. So we were comparing 4 different metals from fairly identical mine processes in 2 different countries. So these are Russia and South Africa. And the indexed process in the Russian information within EchoInvent is simply the extraction, so the energy cost of bringing the material out before it is refined. And then the latter one, which is not obvious in South Africa, is the extraction as well as the refinement. And what we decided to do was compare the extraction versus the extraction and refinement to see if there was any data that we could extract from that would tell us whether any of these were worse players in terms of their refinement costs. And we then came across this funny 6.24 constant, which kept following us about. And what we sort of assumed from this was that what the people reporting this data were actually doing was they weren't fairly comparing metal extraction and refinement on a metal basis. They were simply taking the average of the plant processing costs and then just putting it across all of the material. So all of the bad actors got to basically get covered up by the sort of better behaving ones, as it were. And then to compare to a second data set, so this is a audit report from EY on the company Nornickel. They need to do this for legal reasons. They're a public company, or as public a company as you can be within the Russian Federation, I guess. But they have data for both the extraction and refinement. So again, we can compare the EchoInvent data for the extraction versus the EchoInvent data for the extraction and refinement data. We see that plus 10%, but it's only about 10% more to refine the nickel, which will become obvious when I show you the next slide. Whereas these figures are similar to what we see here, again, about a 6 times constant present in this Russian data. And what's also important, which isn't listed here, mainly for space, is that some of the other data listed within EchoInvent for palladium is simply an average of equal sort of contribution. So there are averages for the palladium market where they literally take the sort of global market for palladium to be 50% Russia, 50% South Africa, and just average the 2 numbers together and have that as a new sort of value when that isn't true at all, because there are 3, maybe 4 players within the palladium market. Admittedly, South Africa and Russia are the 2 biggest ones, but they don't make up the entirety of the market. And there are other sort of recycling processes and other things that don't get sort of taken into here. And there's another sort of food for thought slide right at the end, which I'll sort of provoke some thought within you afterwards. So yeah, this is the hellscape. This is sort of trying to make sense of this. When you run a mine, you usually have something that you can extract at relatively low cost that keeps the lights on, and then you usually want to sort of skim off things that are a bit more valuable. In this instance, we have a nickel and copper sulfide mine. So this is very similar to the process run within Nornickel and similarly in parts of South Africa, where you'll essentially have your material. You'll have to refine this, so this will go through a process. The gangu is sort of what has been termed as pre-slag for anyone that knows what metallurgy. So slag is the stuff that when you melt metal, you skim off the top and it's essentially wasted product. The pre-slag is the stuff you don't even want to bother melting. You want to just get rid of that because that just adds cost. But within the first 2 or 3 steps, we engage in a step called flotation, where we basically stick molecules, usually xanthate, so these are things that contain sulfur, which bind to the nickel or copper, cause it to float out into the metal, and then can be skimmed off, and that can be refined separately. And then what happens is you have a high PGM containing matte, which then has to go through this insane sort of flow chart to try and extract various precious metals, which all add costs, specifically emission costs to them. So there's things like ammonium chloride, ammonia, there's some hydrazine in here, there's like zinc metal reductions, there's zinc, other salts, there's sodium nitrate, there's all kinds of other things which don't get sort of talked about very much, but you have to use these materials. They aren't in your product, they get used and then either sort of burnt away, evaporated, and then there are other heating costs and other things. yeah, it's a bit of a nightmare. It's lots of energy that goes into this and then doesn't really get talked about very much either to get these materials out at the end, which is again why they have such high emissions. So to talk a little bit about the lazy average problem, the issue I have currently is that there's sort of a lack of nuance or supporting values a lot of the time. So you have to basically find primary sources, and there aren't usually very good primary sources unless you can find, like I was alluding to earlier, like the EY audit. So where a company has gone in and validated findings for legal reasons usually. And essentially what the refinement flowchart implies to us is that the emissions are average, as I said earlier, and they aren't a like-for-like comparison, because you're going to be producing a lot more nickel than you are palladium and all these other things. But also because of this, you're going to be putting in a lot less work to actually process those like equivalent materials, because of the fact that you have lots versus a little and the amount of steps you have to add in. Essentially, there also needs to be an emphasis on there being good data, not lots of data surrounding emissions. So I think Ian touched on it, that if you go into EcoInvent, there'll be sort of 15 to 30 different things for one thing, but then there won't be anything for the thing you want. And it then means that the thing that you want, you have to build from first principles or figure out a way to build that. And that isn't necessarily the way that is actually done in industry. So you're having to make assumptions, which is where this sort of idea came to me, where we need a metric of certainty, not too dissimilar from how we used to essentially rate mortgages within financial institutions, where you could say that a carbon credit rating of 5 or a carbon metric of certainty of 5 is very good because the error bars on it are very small. All of the data is primary sources. We know this because X, Y, Z. And then a rating of 1 would be something where the error bars are enormous. Lots of this is made on assumptions, and it's not actually how it's been made, like historically or even now, which I think is a key thing that we need to understand here. And then there's things like geopolitics and the fact that we need to require sort of a knowledge within the area before entering it, or have a very keen interest at the very least. And the fact that there's also a lack of supporting information. So one of the things I'm going to briefly talk about, as I've alluded to the sort of Russia and South Africa for producing metals, it is, I'm not sure people are very aware, but South Africa is in a bit of a crisis at the moment, and the US like Department for like minerals and other things did an assessment, and they basically found that 63 million out of the 70 million, so 90% of the reserves for all PGMs exist within South Africa. The two largest producers of these materials is both Russia and South Africa. And within the current state of South Africa, so South Africa is currently collapsing because of the failure of the energy grid and some of their political systems. The state energy company collapsing is responsible for over 90% of the country's energy, and they're having to engage in something called load shedding, which is where the company intentionally doesn't provide energy for up to 12 hours. So there's rolling blackouts, and these are universal. These affect both like citizens and companies. So you can imagine if you're one of the refining companies, you're going to have to start implementing sort of dirtier practices or finding other ways to make sure that you can keep producing materials. And the old coal factories that they're currently using, the state company that is, are essentially falling into a state of disrepair and are failing to support both the population and the economy as a whole. And another thing that doesn't get talked about, and is a little bit covered in the equipment, but not really, is that this South Africa, for example, because of the fact the country is essentially entirely dependent on very low grade, very bad coal for its power generation, it is the largest SO2 emitter in Africa. And I think now currently the world. And SO2 is obviously very bad because acid rain, and that has knock-on effects and problems, which again doesn't really get talked about. Yeah, so this is a crisis that I see potentially having knock-on effects, both in terms of within South Africa, because the companies that are going to be producing these materials are going to be taking local energy away from the population, because they'll have to be buying petrol or diesel to power generators to cover rolling blackout schedules and all these other things to make sure they can keep turning things out. But then their emissions for these materials are not going to be based on like actual real world data that's currently taking place. And not to go too doom and gloom, I'm going to show a nice example of something as well, because otherwise I'll run everyone out. So this is something that's quite nice. So when you find data like this is sort of a hidden gem, as it were. So this is a press release by Nornickel. So this is where a lot of the data I showed you earlier has come from. So the data highlighted in orange is sort of the key parts. So they highlight here essentially all of the materials that they produce, and then the kilogram per kilogram, or in some cases kilogram per gram, or ton per kilogram, if you will, CO2 emissions for each of their materials. And the last section at the bottom, they explicitly state that they are the world's largest producer of palladium and high-grade nickel, and a major producer of platinum and copper. And then they also say that they produce these other things that then support our evidence that we talked about earlier, where they're essentially skimming off things like rhodium, because they have very small amounts of it, but it takes an awful lot of energy for them to actually refine it and deal with it. So it's not really their primary source of income. It's just there, so they sell it. It's worth an awful lot of money. Yeah. So I will then move on to what Catalytech, so we, our team within Catalytech, are sort of proposing that we do. So we're currently building an internal database, so I'm not showing it due to IP reasons, and we also suffer from issues surrounding the having to start from first principles for quite a lot of simple reagents. And also it might not actually be. So if I buy something from one of my suppliers or a catalog company, I don't know how that's been made in the same way that I can propose. So I need to basically speak to some of my suppliers to understand how things are made to help build better models for the materials we use. And also just stressing that it's very important, which is why I'm spending quite a lot of time at the moment doing this. It's very important for us to quantify the various CO2 emissions of our products, both in terms of investment and support from the wider public, and obviously for our customers, because some of our customers have already started doing life cycle assessments and other forms of assessment on nickel and have found that it makes huge impacts, over 50% in some cases for the CO2 reduction just for swapping catalysts, which is very important. Again, as Ian had mentioned, when you have 97% of your emissions that are sort of from that phase 3, if you can suddenly swap your catalyst or reduce down something from within your supply chain, it makes a big difference. So what is my wish list? So other than sort of hinting at the fact that I can foresee within the next 5 or 10 years that there'll be sort of a chartered carbon accountant role as like a job for the future, my main single wish is that it would be incredibly useful for the health of the chemical manufacturing industry and its wider communities and ecosystems that it serves if more chemical information were made available surrounding the production emissions. So this could be origin, route, and materials in an open source or accessible database, or even a plugin tool, because I can foresee a future where you're using something like ChemDraw, other sort of chemical software is available, but you could right-click analysis and get a CO2 emissions output, or even in Reaxis or something similar, you could get emission data from within that as part of the plugin tool. So I think it'd be incredibly useful. And I can't really overstate that. And it doesn't even need to be sort of cutting edge materials. I would just like more access to basic starting materials so that I don't have to start my route from a very simple molecule, and that very simple molecule have to be from first principles. I would like to get at least 2 or 3 steps in before I have to start thinking about things again, rather than get 2 steps in and realize that's not feasible because I can't find the data for something later on. Yeah, all right, enough from me rambling, because otherwise I'll speak forever. Let's hear from someone else.
Thanks, Elliot. That's great. Thank you. I'm just going to hand over quickly now to Rory Primrose, director from Firefinch Software, who's going to talk a bit about the software development side of things. So over to you, Rory.
Great, thanks, Kim. Let me just present this. See that okay?
Yep, looks
cool.
Good.
Excellent. Cool. Yeah, so as Kim said, I'm Rory. I'm a director at Firefinch Software, and we've helped to build out this prototype version of the app. So I'm going to start off with a quick overview of what we do as a company, and then get into a bit of information about the application itself. So, who are Firefinch Software? So we're a software consultancy. We specialize in the life sciences sector. We've been IBioIC members for a good few years now. Quick bit of history. So we've been going for 6 years now. Our founders originally worked together at a life sciences startup producing a lab instrument, which was later acquired by a large multinational. spent several years there basically as an internal product development team, and then decided to take what they were doing there and offer it to the wider life sciences market. It's been going pretty well, so we've grown to 18 people so far. We've had about 30 customers, a variety of universities, multinationals, SMEs, and then actual startups and spin-outs. So what kind of things do we do? So a bit of what we're going to talk about today. So our bread and butter is product development and consultation. So that can be producing a prototype, particularly for startups and spin-outs. Maybe they've got an idea or some novel IP and we need to turn it into something they can actually show to investors to get further rounds of investment, get it to market. Sometimes it's commercialization, so actually moving stuff up technology readiness level, getting an MVP out the door and so on. For more established companies, it's often adding existing features to an existing product. And there's two main things we do there. So some's actual managed development, like we did in this project. So that's providing a software development team, project manager, etc., and working directly with the client to work out their requirements and then build the product. And in some cases, more consultation. So perhaps someone is hiring for their own software team or building a product for the first time and they need guidance on what processes to put in place, perhaps some architecture support, assistance on how to comply with certain regulations in the field and so on. Secondly, we do a fair amount of business process automation work. So this is often, again, when people are scaling up. So perhaps they've been running their business off spreadsheets, perhaps a lot of it's still paper-based, and maybe that's not going to continue scaling, or if they need to improve their record keeping for QA and QC reasons, for example. And lastly, we do a fair amount of data analysis work. We've got a lot of in-house experience around algorithm development and signal processing. So sometimes this is in isolation, helping people, say, take a IP they've developed in an academic context and give them a clean version that they can use for their startup. Sometimes it's part of overall product development work, and more of late, there's also machine learning work, which is obviously getting a lot of focus at the moment. So let's talk about what we did for CSUM specifically. So as Ian discussed earlier, part of where it came from is there's a lot of people, particularly in the IBioIC network, where their product or service has a justification that's got a lower carbon impact than existing competitors. It can be quite tricky to demonstrate that. So one way to go is to get external consultants to review your process. That can be expensive, and you basically end up with a snapshot of your process. So then if it's something you're developing, if you're tweaking or changing it, you're going to need to get that reassessed. There is tooling out there to let you do this, as Ian mentioned, but it's complex to use and in some cases quite expensive. So we engaged with IBioIC to do two things. First up, we produced a report which basically looked at the existing ecosystems of what tools and data sets are out there to help validate the concepts behind CSUM. And then secondly, we built the app. So as Ian mentioned, there's a lot of credit to Megan here. So she originally built a proof of concept using a language called R, which is great for sort of stats and mathematical stuff. And then Shiny, which is a way of building a web interface on top of it. This is great in some contexts, but it's not what you'd probably choose to use for a production web app. So we basically re-implemented it in a different stack and extended the functionality quite a lot to create the tool we've been discussing today. So we'll kick things off by a quick discussion about what the report found. Some that's been mentioned by the previous presenters, so I won't go into too much detail. But basically, if you're looking at doing LCAs, you've got two main choices. OpenLCA, which is open source and free to use, which is great, but it's very complex and it's basically targeted at academics. And SimiPro, which is a paid product, it's somewhat more user-friendly, but still complicated, and basically assumes that you're either an academic or a professional working for, say, large industrial companies doing LCAs day in, day out. It's also been mentioned, there's a lot of data sources out there. So eConvent's most widely used, but there's a lot of other data sets. Quite a lot of them are commercial, you need to pay for them. And a lot of them are focused on sort of specific sectors. So say the construction industry, for example, has got a big focus on LCAs, so there's a lot of data there. Off the back of the report, basically we've included, but yeah, there's ways you can perform LCAs with existing tooling, but it's not really suitable for, say, SMEs or people who don't do it day in, day out. And there's definitely value in the CSUM concept of a product with a simplified workflow, nice user-friendly interface, and that was focused on carbon accounting and biotechnology sector. So we started developing the app. One of the key things that we built into it was this ability to compare different processes. So like I was talking about, if you're designing your process, you often want to think about things like, if I make this vessel 10 times bigger, what's that going to do to the process? If I change from one feedstock to another, then how will it change things? Perhaps there's two fairly different processes with the same end result, and you want to just compare across both of them. I'm aware that Ian showed a screenshot of the app earlier, but you've not seen the actual app, so I'll quickly show that in a second, I think. But just briefly, what did we actually build? So a web app is the most suitable way for this to work. So it's a cloud-based tool, it's multi-tenanted, so you can have different companies using it, and long-term people will be able to collaborate on their process models. A key part of it is what Ian showed in his screenshot, so an interactive visual tool. So if you're wanting to model it, you can nicely say, here's my inputs, here's my equipment, put your energy mix in, all through a nice visual interface. You've got the ability to compare and contrast between different processes, and then get automated reporting out the back of it. So if I just jump across quickly to my browser window. So here we go. So this is just a demo instance of it. So I've got some made up data in here. So I'm in some client with a project, and I've created two very simple bioprocesses. So if I click into one of them, I get this nice interface. So basically on the left, you've got a list of different kinds of things you can model in your process. In the middle, you've got this visual editor. And on the right, you've got the ability to edit properties of each of these. So let's say I want to add in some new external data, which comes from EcoInvent. I can drop it in here as a source. I can start typing in here. So let's go for palladium, just because it's an example discussed earlier. And you get a little list of all the palladium data we've mapped in. As was mentioned, basically, the entries you get are going to be either global ones, which are these sort of averages across different markets, South African ones or Russian ones. And the Russian ones are effectively the ore, whereas the South African ones are actually extracted and refined. So I could drop that in. I could say that for some reason we're combining palladium and sugar beet in a masher. Don't know why you do that. And you're getting your end product. So obviously this is really simplified, but you'd model out your whole process, you'd save it, and you'd hit analyze. We've built out some very simple analysis here. Part of refining the product will be to put in more useful stuff based on user feedback, but you can get stuff like breakdown for your product where your greenhouse gas emissions come from. In this case, based on the dummy data I entered, is basically all coming from the sugar beets coming in. Something really handy, which I think I've seen a few people asking about in the Q&A, is you can compare across processes. So I can take this bioprocess, compare it to an alternate one, and hit compare, and then I get a comparison of the emissions for the two of them, which is great if you're playing around with, say, ones if I use sugar cane instead of sugar beet, for example. I think that's basically all I want to demo there, so I'll just go back to the slides. Cool. So what did we do? So we sat down with Ian and Megan at the start of the project and basically came out with a map of how we thought the process would work. This is really useful to have as a reference, but one of the great things with developing software is you can refine stuff as you go fairly cheaply. So it's good to have a plan, but if as you develop it and test it, you change your priorities, for example, then it's easy to deviate from it. So what's illustrated here is largely what we've ended up building for prototype, but one example that's changed is initially we planned in prototype to let you configure different external feeds. Instead, we reprioritize stuff, so it's only integrated with eco-invent, so we could spend some more of the effort elsewhere. And similarly, we produced some mock-ups, basically as a discussion point. As you'll see, we ended up with something fairly close to this in the actual built product, which is good. So, a bit of technical detail, and where most people on this call won't be particularly technical on the sort of software side of things, so I'll just keep it to a high level. So the demo app I showed you there is running in Amazon's AWS cloud, which is great. It gives you a nice scalable cloud infrastructure, so as more people come onto it, we can allocate more hardware to it, keep it running nice and stable. And we're using just a simple relational database provided by AWS as well. There's no inherent dependency on it, so if anyone ever wants to shift to another cloud provider like Azure, for example, or have a private instance of it, we're not tied into anything proprietary of AWS, so that'd be easy to do. The software stack. So as I mentioned, the initial app was written using R and Shiny, but we re-platformed that. So we used a great tool called JHipster, which is an application generator, which lets you really quickly scaffold modern web apps. It's not something we're going to use long term, but for this sort of prototyping work, it gets you up and running really quickly for the code base you can then iterate on later on. The front end you saw is using React, which is the most popular choice for web apps at the moment. So if you're, say, hiring for developers, there's loads of them on the market, there's lots of support out there, it's well documented. And one of the great things about it is for that visual editor I showed you, there's a open source node editor called React Flow, which gave us a lot of the fundamental entities we needed to build it out, so we weren't building the whole thing from first principles. A couple of things which would be great to do to the app in future phases. So as I mentioned, it's only based on the eco-invent data at the moment. The way we've architected it, you should easily be able to integrate in additional data sources. Is basically you just need a mapping exercise to get from their data to the categories we've got. And also at the moment, the only way to get data for a process into the application is through that visual editor, which is great and very approachable, but for more advanced users, it'd be good to also have more of a raw data view to allow you to just paste in data about your process. Particularly say if you've already got spreadsheets or something modeling it, it's going to be easier to map that across that way. I've got a few notes of just about sort of data toward the end of this. So I asked the lead consultant, Rich, about it, what the main technical challenges were when he was working on the project. And interestingly, most of the observations weren't so much about the technical difficulty of the software itself, but touched on similar points to the previous talks around basically data quality and how you handle it when you're modeling a process. So eco-invent's great in terms of there's loads of data in there. There's some that's got like really minute precision and it's covering like very specific things. If it's got the exact thing for process you need, that's great. If not, you're often going to end up basically falling back to doing stuff from first principles or using averages that maybe aren't very accurate or appropriate to use for figuring out your carbon footprint for a process. So we do support handling this in the application. So as you may have seen when I was showing the interface, for the eco-invent data, I dropped in a box to point at an external data source, but you can also just stick in inputs and then manually enter in the footprint data yourself. So you can figure that out using estimates and engineering rules of thumbs, etc. This works okay, but when we started the project, we hadn't realized how reliant people were probably going to be on this. So it's something we will look at simplifying and making more user-friendly in the future. This last slide is somewhat touching on similar points that we discussed previously as well. So the actual technical process behind the scenes for working out the carbon footprint isn't that complicated if you've got the data in your process modeled. It's effectively addition. Your main problems are actually getting decent data. Questions about like how that data apportions carbon footprints. So there were some examples earlier, but taking another one. Let's say you're working in the dairy industry and you're selling dairy products. So you'd be attributing the whole carbon footprint of your cows to those products. But then you start selling the leather from those cows, which you consider a byproduct. Do you reattribute some of the carbon footprint off to the leather? Do you keep it all against the main product you're selling when you've effectively got carbon-free leather, allegedly? There's not an actual technical answer to that. It's something that's just a political thing you need to discuss. Averaging doesn't work. That was touched on earlier. I won't go into too much more detail, but yeah, a lot of eco-mem stuff is basically you take data from, say, South Africa and Russia and average it to give you a global value. And lastly, so let's say you're modeling your process and you're figuring out what your carbon footprint is, and you get to the end of it and you come up with a figure. People are going to want to know that that figure is valid and justifiable. If you've modeled it, the data you've used is going to be confidential. If someone knew it, like say someone you're supplying to, they know exactly what your costs were and what your margins were, so you don't want them to know that. So this is somewhere where, say, if CSUM became a widely accepted tool, it could be great. So if you're able to say, we modeled our process using CSUM, here's the end results and a report produced from it, and then people had confidence that those values were correct, but you didn't need to give away your underlying information, then there'd be a lot of value there. So that was a quick run through of what we did. Here are my contact details. I'm always happy to have a chat with people. So feel free to get in touch if you've got any questions, and I'll be around for the Q&A that's following shortly as well.
Thanks, Rudy. That's brilliant. Good to get your perspective on things there. I'm going to hand back quickly to Ian. I think, Ian, you're going to try and run through some of the Q&A and maybe have some comments as well on what we've heard.
Sure, yeah, and Elliot and Rory will be very happy for you to jump in if you want to add into this as well. So I think what was clear from what I said and also from what Rory and Elliot were saying as they went through their presentations, just how tricky the data is here. So there's a couple of questions in here, I think, around about how this fits in with the wider kind of life cycle analysis approach. So I think, and there's a few areas in here. I think so. David mentioned a comment around what happens to the carbon that's captured in seaweed and then it gets re-released back out. I think that's a very valid point. And I think, Rob's made a comment about, thinking about downstream process, the downstream scope, the scope 3 emissions as well. And it's becoming, as people consider circularity, that is becoming much more important. And there are a couple of people who have asked kind of related questions. And this comes back to what actually it was kind of a sort of little joke, an in-joke I put into my title slide, is that I don't think what we're doing here is carbon accounting. I think what we're doing here is carbon bookkeeping. I think we're doing the fundamental calculations around a particular stage for the thing, and we've actually actively tried to avoid becoming life cycle analysis. This is just a number that can be fed into a wider life cycle analysis, and then it comes into Rory kind of made that comment earlier when he was talking about the dairy industry and where you might be apportioning between different products. You have to do some apportioning here. Certainly when you're thinking about waste materials, especially if someone is actually maybe valorizing some of the waste that you're generating. But what we're trying to do here genuinely is not around the accounting side. It's more the bookkeeping. So in my head, and I might be doing a very big disservice to accountants and bookkeepers here, but a bookkeeper is the person who calculates the fundamental numbers. That's what we're doing here. Potentially even from the fundamental thermodynamics of how a process operates. And then an accountant then, and that's the equivalent of someone who's totting up the numbers in a bookkeeping sense. And then an accountant works out how you can apportion those numbers to either pay, the minimum tax or however it might be, the accountant's role. They're doing something which is actually, I think, much more subjective than objective. So I think I hope that answers the question around why we are trying to limit where we are in this. We're not trying to be life cycle analysis experts here. We're trying to develop a tool that companies can use and actually academics can use as well in justifying and working and in understanding what the impact of their process within very specific boundaries might be. And I'm happy to be grilled on that, but that's just to make it clear to people. That's kind of what I wanted. That's what I wanted to get across. I don't know if Elliot and Ruru have anything to add on that one. If not, I can move on. I will do, and you can chip in a second if you want to, guys. And I think there's one very important point actually that Anne Connor mentioned on here around using Echo Invent. So I should stress that this is effectively a research project. We're not using this for any commercial use. And at some point, when this becomes a commercial product, we will be using a commercial version of the Echo Invent database. At the moment, it's actually using an academic license. And that's something that I should stress when we are working through this on real examples. This is development of the technology. It's effectively a research project as it stands at the moment, and we're moving to something broader than that, that's more commercially focused. It will be a different licensing model for using those for using the background data set. And as I say, there is an irony in that background data set, is that I actually don't think it's not really good enough. As it builds up, it will get, ironically, we will be adding to that data set with the more work that we do. So I think that's an important point. And there's a couple of questions from one from Shiwen and one from Sarah at Croda around scale, and I think that's something that's worth following up on. And I think it partially, this depends on what data it is you're using. If you're using real data from the plant, you obviously don't have that issue. I think we are well practiced in the chemical industry in terms of, as I mentioned, around reaction calorimetry in scale up, so that we do understand that things you do when you do calorimetry, and you understand the heat evolved from a process dimethyl malate to butane trial example I showed. We've got data on that one, which was actually measured in a calorimeter at very small scale, tells you how much energy was being released from that process, and that can be extrapolated to larger scale. So that's kind of some of the assumptions in here. But really, I think these are at the moment, we are using things like engineering rules of thumb and predictions that are commonly used throughout kind of chemical engineering, process engineering, to estimate what happens as you move from small scale to large scale. But I do accept that's potentially a challenge. But I think this can also be used for thinking about what the optimum emission, what's the optimum for of scale in terms of emissions. So what scale do you have to get to kind of minimize those emissions to make that more appropriate. And I'm just kind of scrolling through, trying to hopefully not picking out where these are. David McElroy has asked a comment here, and this is a really good one, about what's the carbon footprint of the kit involved in the process. And I see
I was just answering that, typing. So I'm typing as you're speaking.
You want to, well, you can chip in if you want, Elliot. I mean, what I was going to say on my one before you jump in there is that when I've talked to quite a few companies around this, and quite a few experts in different companies, including GSK and Croda, about how they approach this, and in particular at GSK, they've tried to do this estimate. So, for example, what is the carbon footprint of the steel associated with all of the fermenters at Irving, for example, and the kit that's sitting around there. And actually, the reason we've not got to that yet, and I would like to have that as part of the tool, it's not in there at the moment, but it's not there yet. The reason why is because when they do the calculations, it turns out to be a relatively small number compared to the other operational inputs. So the energy associated with the raw materials, and the energy associated, the emissions associated with the raw materials, and the emissions associated with the energy use tend to dwarf the emissions over of the kit that goes in. And it's a bit like, I guess, the equivalent of running a petrol car versus an electric car. The initial car, the initial carbon footprint of the electric car is higher than that of a petrol car because of the battery technology, but and there's smaller manufacturing operations, and over time the operational things overtake the total emissions. So I think the answer really, David, is that that's as far as our understanding is right now, that's a very small number compared to everything else, but it will become part of the tool. Initially, though, it will look a bit like, well, how much steel have you got? And it will be prorated for the amount of steel in there, and some calculations on what the additional emissions associated with turning a lump of steel coming out of steelworks is into a reaction vessel. So there's I'd say that's kind of a phase 2 there. But Elliot, do you want to jump in?
Yeah, to jump on the end of what you were sort of just saying. So I'm hoping that what I've said to that answer or typed in the answer makes some sense. You can sort of see this as like a sunk cost, or if you've ever, or within companies, whenever you buy equipment, you'll often cost them over their lifetime. So the expected amount of time you want to use the bit of kit. So say one of the bioreactors you're going to use over a 25-year lifetime, you can look at how much that's going to cost you in the steel production, how much it's going to financially cost you, and then over a 25-year rate of use, you can say every year it's 1/25th of this input until it eventually gets decommissioned. Similar to how nuclear power plants work, where we calculate their emissions, because again, nuclear is one of the lowest carbon emitting energy sources, but you've still got to build huge amounts of concrete, put everything within it, and there are costs associated with this. But then the thing runs for 20, 30, 40, 50 years. And as Ian was saying with the car, it depreciates. It's something that's gone. And ultimately, we still need stuff. Like, we still need to build things. And companies are also going to be hesitant to just piss away money on things just because they can build new things. They have to be cost effective. They have to actually get something from it at the end of the day. So we still need to make things, and the kit still needs to be produced and used within the process. It's just a case, is it cost effective to do it? Is there a better way of doing it? Okay, this thing is going to last 20 years. That's fine. Cool. It's not going to last a year and then to buy a new one or something. Yeah, it's the sort of straw argument, or using like a purpose-built tool or pipes, or just purpose-built things rather than cheap and cheerful alternatives that need to be bought and repeated over and over again.
Okay, so there's a couple of questions I think in here as well about limitations of of our carbon accounting tool compared to other tools as SimmerPro, and I don't think they're actually very fair comparisons. I think I actually think something like and the word has just escaped me, the main chemical engineering software that people use is probably quite appropriate for doing something like this. So what we're doing here is a mass and energy balance, and then linking that up to emissions associated with those. So it's more of a chemical engineer's technique. What we are really trying to achieve here, though, is something that can be used. So I would say SimmerPro is a tool that is used by experts, by people who consider themselves LCA experts. We started this process to develop a tool that could be used by development scientists and development engineers working in real systems. I didn't want it to be something that is only in the hands of LCA professionals, and so things like SimmerPro and OpenLCA, and we tried. I mean, that was our first port of call when we started looking at this. Could we use those tools to develop the kind of thinking and calculate carbon footprints for companies in the IBioIC membership? And I think that initially the simple answer was we weren't technically capable of doing it, and then actually we've had through this process, and as Rory mentioned, the work that Rich did comparing what we're trying to do here to those ones. Rich actually looked really under the bonnet at a lot of these tools, and we came to the conclusion that these tools can't do what we're trying to do. They don't do that bookkeeping part. They rely on information that's already in the databases, and if you can't trust that data, which I hope we've made it fairly clear that none of us are particularly enthusiastic about the data in these data sets. If you can't trust that data, then actually you have a fundamental problem that you might get the most beautiful visualization of where your emissions are coming from using SimmerPro, but actually it's all built on fairly shaky foundations because the underlying data is so weak. I'm starting to become convinced that actually you have to do this bespoke for every single operation, every single manufacturing operation to get a real number for each one. I don't think average data really works. I think it's going to be really difficult because as there was a question there that I think that Elliot's already answered from Shiwen about how different geographies affect this. There will be a very different approach to, even if you took identical processes that were operated. Let's say we're looking at that seaweed process operated off the coast of Scotland versus operated off the coast of somewhere where they might be generating all of their electricity from coal, then they're different footprints for the same product. And so I think each plant has a different footprint, let alone each country or route to that product. So I think that's a challenge for us. But fundamentally, what I want this to be is something that eventually can be used by regular process development scientists. We don't have to pay £25,000 to get a life cycle analysis done for projects. We can spend a day at our computers working through some examples, getting data where we have, estimating data where we have, much like we would have to do if we were doing a cost model, and then use that data quite early on in process development to say, look, this one looks significantly lower in carbon than that one, and the cost impact of it being lower carbon isn't significant, or whatever it might be. And actually, I don't know if people noticed, but when Rory put through the to show this little demo there actually is a cost model built into this anyway. So there's a really clear opportunity in there, which is that you can put in a price of carbon and actually just link everything into a cost model if you want to, because you can just put in a number for the price of carbon, and that will give you a feel for where that would look. So I know a lot of companies are already pricing in carbon. We can do that in here, and that then links together the carbon and cost models, which is quite a nice feature. That's what we'd like to be able to do. Hopefully that answers that question. I would just like to say that the last bit, just one last question from Senem there. And I think Senem, I think it would be a good question. If you want to give us a shout, get in touch with us. We can talk through your question here. I think the issue, so this is a question around how you can use, how we can do carbon footprints of mammalian cell line production. And yes, I think that's a really good opportunity here. Actually, I think that'd be a really interesting challenge for us. One of the biggest problems we're going to have with that is, again, it's going to come back to the fundamental data, the embedded carbon of those of the materials that are going into that process. So there's quite a lot of back calculations are going to be needed for that one. In terms of, you're talking about metabolic pathways in there, actually we'd view it as a kind of black box system. We would say, right, that's the fermenter, and you'd work it out per litre of culture or per whatever, or however you wanted to operate it, per milligram of product made. You wouldn't necessarily worry too much about what's happening inside the cell. So and the one last thing I was going to mention actually was just to kind of link what Elliot was talking about on the tool that we've seen here. What Elliot's really shown you there, I think, is essentially what's under the bonnet of CSUM. That's the kind of underlying calculations. That's how it works. That's how I wanted Elliot to come and give this presentation. It gives people a good feel for how these calculations are put together, and hopefully means that when you come to use our tool or use it with us, guiding you through it, you don't have to go into that detailed spreadsheet model. You've got something which is a bit more user-friendly. I think hopefully that's covered everything, Kim. And if we'll look through the questions, I think, Kim, and we'll try, and anything we feel like we haven't answered properly, we'll try and
yeah, absolutely. As ever, we've kind of run out of time, but if we'll look through the questions after the webinar finishes, and as Ian says, address anything that we didn't pick up on there. So very quickly, I'm going to do a plug of the next BCB event. 1 second, just share my screen. So we're running an event on the, can everyone see that okay? We're running an event on the 14th of September with the Chemical Industries Association, looking at the role of biotechnology in net zero chemical manufacturing. There's a QR code there. You can register using that or on our website at www.bioeconomybuilder.com. And yeah, thanks to everybody. Thanks to all the speakers. Thanks to everyone for joining us this morning. Hopefully welcome you to another webinar in the future. And you can contact me if you have any questions. My email address is on the screen now. So thanks, everyone. Have a good day.